Okay, let's see. What did you say? So again, matrix multiplication, now that I've jogged your memory, hopefully it's easy, and you remember what these things are. All right, everybody got 1 for the first thing. The first number is indeed 1. You can see it's 1. I like this way of doing it. So you got 1 copy of this, and no copies of the previous one. It's a 1. The next number is, all right, everybody got it this time, 2. That's exactly right. Very good. What about the one after that? So you applied it once, you got 1, 2, and now you're going to apply it again. You got the vector 1, 2. So now you're doing A applied to 1, 2. Okay. What does the matrix A do? Okay. 1, 2. Let's see if you guys figured it out. You get 3, exactly right. Okay, so it's something 3. And why is it 3? It's the sum of those two things, right? If you look at the bottom here, the fact that there's a 1 here and a 1 here says sum up the two coefficients before. So the bottom thing here is the sum of the previous two. Okay, hold on. Maybe I'm confused. Okay, yeah. So 1. Okay, let's write it out carefully, and let me do it on the blackboard now that I have a charger. Thank you very much for that. And I have a pen. Okay, so the matrix A, let's see what it does to x, y, right? That's the matrix 0, 1, 1, 1 applied to x, y. So the first component is y, so it sort of shifts the y up. So the y goes from being in the bottom to being in the top. I'll turn this thing off, okay? Right, the y kind of moves up. That's exactly what this 0, 1 over here means. It means 0 copies of the x and 1 copy of the y in the top. So the y kind of moves up. And what do you get down here? You get x plus y. So the y moves up, and then you combine the x and the y together to give you that term. So what is this matrix doing? It shifts everything up, and then it takes the sum of the two terms and puts it down. So if you do that correctly, if you apply A to 1, 1, you get the first one moves up, right? This one becomes this one up here. And then you get a 2, with a 1 plus 1, which is a 2 on the bottom. Okay, and then you apply A to that. So A squared on 1, 1 is A applied to 1, 2. So what is that going to be? Well, the 2 is going to shift up, right? So this 2 on the bottom goes up here, and then you get the sum, 2 plus 1, which is 2, 3. All right, so I don't know what you guys actually said. Did you is that what you said with the 2, 3? Let's see. Okay, so 1, 2, okay, very good. 2, 3, very good. And then the next one is 3 and 5. Okay, people, I think I've figured out the pattern. Okay, great, very good. So A cubed applied to 1, 1 is the same as A applied to our previous result of 2, 3, which is 3 and then a 5. 5 coming from 3 plus 2. Okay, this 3 became that 3. I guess this 3, not the best 3 I've ever drawn. Let's try to fix that up a bit. Okay, 3. Okay, so there you go. That's what the matrix is doing, and that is the answer. I think most people figured it out. Did we get all the way down here? Show correct answer. 5, 8. How many people got the 8 at the end? Ooh, right around 70% of people. If you got a 5, you were sort of off by 1. So close. Okay. So what is this matrix doing? It's calculating the sequence. What on earth are we doing here? Why do we care about this matrix? What does this have to do with anything? This matrix is actually doing something very cool. Does anyone know what these numbers are and what the pattern is? Yeah. These are the Fibonacci numbers. These are the Fibonacci numbers. Fibonacci numbers. So if you look at what we're creating here, we're making the sequence 1, 1, 2, 3, 5, 8. That's what we've done so far. And these were the entries of the matrix to some power. This was a to the 4 applied to 1, 1. This was a to the 3 applied to 1, 1 with these two numbers. And so our matrix, what it does is it calculates the next Fibonacci number. So every time you do another matrix power, you do a to the 5 of 1, 1. That will be 8, 13. So this matrix is secretly computing the Fibonacci numbers. Why am I telling you this? The lesson of the last few weeks of this course is that everything is vectors, or everything can be vectors. Everything is vectors. So even something like the Fibonacci numbers you think of as a sequence of numbers is actually secretly something to do with vectors. And you can calculate them with this matrix power A. Later on, we're going to see things like images are vectors, like images. Images are vectors. So when you have like facial recognition that uses vectors. Even things like words are vectors. Words, sentences are vectors. That's how ChatGPT works. So we're going to learn about this as well. And so these last few weeks, we're going to tell you, thinking of things as vectors, what can you say? And we're going to start with this thing called PCA, which hopefully you watched the video. And it is a way of taking stuff with vectors, think of your data as a vector, and then you can do stuff on it. So the first lesson is that everything is vectors, including data. And the second lesson is you can do magic on vectors. You can do magic on vectors. And this magic is sometimes just like mind-blowingly impressive. And the thing I want to start with is you have the Fibonacci numbers, and you might think, how much work is it? Let's try to calculate the 100th Fibonacci number. Let's try to calculate the 100th Fibonacci number. Try to calculate. And you might think, okay, to calculate the 100th Fibonacci number, you're going to have to add these things up 100 times. You're going to have to do 100 units of work, 100 additions and subtractions and so on. And that's because you need to calculate a to the power 100. That's going to be 100 matrix multiplications. But there is a super sneaky secret way of using vector magic to calculate a to the power 100 doing almost no work. So you can calculate this. Calculate without doing 100 units of work. This is like some sort of weird secret magic that lets you do this instantly. And I want to see if you guys know what it is. If somebody says, please calculate a to the power 100, other than doing 100 matrix multiplications, what could you do? And I made this a mathematized to see what you guys know. What's a sneaky magical way to compute large powers of the matrix A? Put down any ideas you have that might help. And this, again, if you had a good linear algebra class, they would have told you this. But maybe in linear algebra class, they just tortured you and said, you do this stupid calculation over and over again and don't think about why. And then you were like, you memorize everything for the final exam and then forgot it. So we'll see if you know or not. So there's a word cloud. You can put in any words you know. If you have no idea, think for a minute. Maybe something will come to you. But if you really have no idea, put in I don't know. And we'll see what you guys think. Okay, I'll give you 1 minute to sort of brainstorm. Feel free to talk to your neighbors if you guys can come up with something together. Okay, time is almost up. Put in your answers. Again, it's okay to say I don't know. But if you really have no idea, let me know so that I know that you don't know. Okay. Okay, let's see. What did people say here? Most common answer was? Ooh, okay, we got some ideas. So this is great. Okay, I don't know. Maybe it's the most common. I don't know. 4 people said I don't know. Okay. This is a great one. Use the computer. Fantastic answer. The thing we're trying to do is we're trying to understand how NumPy works, if you want to think about it that way. The people who invented NumPy had to know how to do this. And in fact, NumPy will break for certain things. You got to know when it breaks and like how it works. So like we're trying to see why it works. Of course, this is true. It's like if somebody says like, how does a car work? Or like, how do you get from one place to another place? You say like, oh, you just go pay them money and they will give you a car. Like, we want to know how the car works. All right, this is great. Diagonals of the matrix. This is one of the right ideas. There's something called diagonalize. So diagonal is a noun. We want the verb form. So diagonalize means turn the matrix into a diagonal matrix. We'll see why that works in a second. So this is like functionally the thing we're going to do. But maybe it's we want to see how it works. Okay, series calculation. I don't know what that means. Eigenvectors is also related to this thing, number 3. So eigenvectors and this diagonalize, these ideas are one of the things that will work. No idea, great. Recursion. Recursion will give you the step that takes 100 things. So it's like you got to calculate a to the power 1, a to the power 2. Every a gives you the next one. So recursion is the slow way to do it. We're going to do the super sneaky fast way. That's just going to give us, with eigenvectors, it's going to be super fast. Okay, eigenvectors and values. Yes, that's it. Okay, yeah, then this person has described what eigenvectors do for us with algebra, which is very nice. So, okay, great, amazing. Okay, yeah, this person too. Okay, so at some level, you can say, this is maybe what they taught you in algebra class, is you write A equals QD Q inverse, and D is diagonal. And then, when you do matrix powers, you do A, let's say you do A cubed. That'll be QD Q inverse times QD Q inverse times QD Q inverse. And now you have a nice thing, which is the Q's cancel with the Q inverses. So the Q and the Q inverse cancel out, and what do you end up with? Is Q times D cubed times Q inverse. So if you can write A with this like weird diagonal Q business, then when you do powers of A, you get powers of a diagonal matrix. And powers of a diagonal matrix are easy. So if D is the matrix, I don't know, what matrix is it? Let's say it's 7, 0, 0, 2. What is D cubed? It's going to be 7 cubed, 0, 0, 2 cubed. So diagonal matrices have easy powers, and if you can write A this way, then it will work. This is totally true, and this is maybe how you were taught in algebra class. But let's see where this stuff comes from, because this is like kind of a confusing, like where did this come from, and who's Q, this kind of thing. If you kind of just like someone tells you do this, it's like why? So the thing I want to do is do it a little bit more slowly, and it's really to think of eigenvectors. So I'm going to notice something about A. I'm going to notice that A times this vector, 1 phi. I'll tell you what phi is in a second. A times 1 phi is equal to phi 1 plus phi. Remember, what does A do? Remember A of xy is shifting up the y and then doing x plus y. So no surprises there. A of 1 phi equals phi 1 plus phi. And this works for any phi. But I want to pull out a factor of phi. So a phi times 1 plus phi over phi. So I just pulled out a factor of phi. And now I want to solve this equation. If phi equals 1 plus phi over phi, then this is the original vector we started with. Then this vector is the same as this vector. Okay? And that is called an eigenvector. That's called an eigenvector. So that's saying if you apply A to this vector, you get back this vector. Okay, you stretch it by a little bit. And so what I'm going to do is I'm going to solve this equation. Phi equals 1 plus phi over phi. This is a very secret, nice equation. Does anyone know what number phi satisfies phi equals 1 plus phi over phi? Has a special name. Let me draw it as a picture. Okay, so here we're gonna make a rectangle, and the rectangle here is going to be 1 by phi. So the ratio of this rectangle is phi to 1. It's a phi to 1 rectangle. Phi to 1. And then we cut out a little square. Actually, no, what do I do? I add 1 to phi. 1 to phi. Okay, yeah, I make it bigger. So this is a phi to 1 rectangle. Phi to 1 aspect ratio. Then you go down, you get 1 plus phi to phi. So make this thing phi. This whole length here is 1 plus phi. And so if you look at this big rectangle, this is a 1 plus phi to phi rectangle. So the little rectangle has a ratio of phi to 1. That's this little guy. And the big rectangle, this big rectangle, has a ratio of 1 plus phi to phi. And so my little equation says these two rectangles are similar. They're the same shape, just one is smaller than the other. That's the phi we're looking for. The phi we're looking for makes it so when you take a rectangle like this, and by the way, this is a square, right? This is a phi by phi square. This is a square over here. This is a square, because it's phi and phi. Then it has the same aspect ratio as the little rectangle and the big one. And you could do this again. You could add on another big square. You could add on a big square over here. Look at this beautiful big square. And that will also be the same size rectangle, just blown up. That's what the phi we're looking for. It's this special number that makes your squares and rectangles work really nicely. Has anyone ever heard of this? Sorry, what was that?
Eigenvalue?
No, it's not eigenvalue. This is something that people before eigenvalues knew. Was this nice phi? It's called the golden ratio. This is the, quote, golden, which the Greeks knew about, and they made all their architecture, supposedly, the golden ratio. Okay, who's heard of the golden ratio before? Okay, now you've heard of it. Maybe. So this special thing is called a golden rectangle. And a golden rectangle has a property. You add a square to it, and it's the same rectangle, just bigger. And you can keep doing this, and then you can even make a golden spiral, where you go and you spiral around like this. So the golden ratio. And so what we're seeing is the golden ratio is an eigenvalue of our matrix. So if we set this phi right, then we solve this equation, then 1 phi is an eigenvector of eigenvalue phi. So this phi is called the golden ratio. You can turn this into an equation which is phi squared equals 1 plus phi, right? And then you can solve phi equals 1 plus square root of 5 divided by 2 by using the quadratic equation. So that's the formula for the golden ratio. And what have we seen is that 1 phi is an eigenvector of A of eigenvalue phi. Amazing. And that's because A times 1 phi equals phi 1 plus phi, which equals phi times 1 plus phi over phi, which equals phi times 1 phi. And that's because the golden ratio satisfies this property that it has this self-similarity where this ratio equals phi. Okay, great. Okay, 1 phi is an eigenvector. There's another eigenvector, which is this, 1 negative 1 over phi. 1 negative 1 over phi. And this satisfies the same thing. It's an eigenvector of A. And its eigenvalue is negative 1 over phi. And the reason is negative 1 over phi is the other root of this equation. So I'll just write it up. A1 negative 1 over phi equals negative 1 over phi, and then you add them together, 1 minus 1 over phi. And you factor out a negative 1 over phi to get 1, and you get 1 minus 1 over phi over negative 1 over phi. And just like the golden ratio, negative 1 over phi happens to be equal over here. And I will leave that as a little exercise if you want. This ratio happens to be this ratio. It's the golden ratio rule written another way. Okay, so we have 2 eigenvectors and 2 eigenvalues. And you're like, okay, well, who cares? This is so dumb. But here's the magic, is that for eigenvectors and eigenvalues, it's very easy to calculate powers of a matrix. So if someone says, please do a to the 1,000, or I guess I was going with 100. Let's do a to the 100. A to the 100 times 1 phi. I don't know how to do a to the 100 times any old vector, but a to the 100 times 1 phi is going to be a to the power 99 times phi times 1 phi. So doing a one time gives you a phi out. Multiplying by phi or multiplying by the matrix, that can go in either order. So a to the 99 times 1 phi. Okay, and I can pull out another a. So phi a to the 98 times phi times 1 phi. Hey, this is easy. This is phi squared times a to the 98 times 1 phi. So doing a to the 100 times any old vector is hard, but doing an eigenvector is so easy. every time you matrix multiply, it just turns into a constant, phi. Okay, so I can do it. I can actually, I can skip some steps here and explain to you that it's phi to the power of 100 times 1 phi. Every time you matrix multiply. So for eigenvectors, powers are easy. For eigenvectors. Powers are easy. All right, great. So if you want to know a to the 100, let's say we want to know a to the 100 times 0, 1. Here is the trick. Here's the big fat trick. Take the vector 0, 1 and write it in terms of eigenvectors. So this will be a to the 100 times something times 1 phi. Let's call this something lowercase a. And it'll be something else times 1 negative 1 over phi. Okay? And if I figure out what those somethings are, then I'll be able to calculate this, because I can calculate either of these. So eigenvectors are the key to sort of simplifying things that look complicated, suddenly look simple if you're doing them with eigenvectors. So I just have to solve for what this is. If you'll notice, the top component here is 0. And here I got a plus b in the top component. So those got to be opposites of each other. So why don't I call them b and minus b? Let's call them b and minus b. So let's call this one, or I'll call them a and minus a. Okay, great. Minus a times this. So what vector is this? I just need to solve a phi plus a times 1 over phi equals 1. That's the bottom component over here. A times phi minus 1 times a. Another way to say that is a equals 1 over phi plus 1 over phi. Very simple. And it turns out this is something nice. This is 1 over square root of 5. So the solution here is 1 over square root of 5. I'm skipping some algebra steps, but they're easy. Okay. So I've rewritten something that I wanted in terms of the eigenvectors, and now I can do the matrix power. So this is 1 over square root of 5. We said every time you do a matrix power, a applied to this special vector, it just comes out with a constant, phi to the 100, 1 over phi. And then you get minus 1 over square root of 5. Phi to the 100 times 1 negative 1 over phi. Okay, so we did it. Look, we did a power, this thing to the power of 100, and I just figured out what it is. Here's a formula for what it is. Okay, and in particular, the top component is, what is it? It's 1 over square root of 5, phi to the 100, minus 1 over square root of 5. This one, I put the value in wrong. It should be negative 1 over phi. Negative 1 over phi to the power of 100. So the top component of this matrix multiplication a bunch of times is this crazy formula. And that is equal to, so the top component of a to the 100, 0, 1. On the other hand, what is the top component of a to the 100 times 0, 1? It's exactly the nth Fibonacci number. So this is f100. This is the 100th Fibonacci number. And I just, through the magic of linear algebra, I just found a formula for it. So the fact that this is the same as the Fibonacci number is how we started. And why we came up with this matrix A was, remember, the matrix A was doing this kind of thing, calculating the Fibonacci numbers. And I guess here I did it with 1, 1. But notice that A of 0, 1 equals 1, 1. So it's like if you're off by 1. So it just depends on how you start. But OK, that's the thing. So what did I do here? Instead of doing a computation 100 times by using the magic of eigenvectors, you can calculate the 100 thing by just turning it into multiplying the eigenvalue 100 times. To me, this is pure magic. Like, we went from a problem that seemed impossible. You have to do it 100 times. And by looking at these crazy vectors, these eigenvectors, you can calculate what it is. Let's see if it works. Let's do NumPy, like was suggested by that student. So let's open up a Colab and make a new notebook here. And let's do it with NumPy. Import NumPy as NP. Okay, so let's make phi I wonder if we're going to overflow this computer. Phi equals 1 plus square root of 5. 5 divided by 2. Oh, look at that. It knows about the golden ratio. Okay. Phi. And let's do, I guess my formula says, if I do, let's do 4n in range 10. My formula says if I do phi to the power n divided by square root of 5 minus 1 over phi. What is this? Okay. Minus 1 over phi to the power n, also divided by square root of 5. Yeah, that's the formula. This is supposed to be Fibonacci numbers. So let's print this out and see if our formula works or if I made a mistake somewhere. Well, it'd be sad if I made a mistake. Okay, hold on. Okay, here we go. So this crazy formula with square root of 5s and this phi number gives you 1.99999999998. Is that 2? I don't know. Is it 2? 3.00004, then 5, then 8, then 13, then 21. These are the Fibonacci numbers, but I calculated them just by doing it, right? I didn't have to do anything. You could skip straight ahead to like 100 or something. So let's call this fn. Let's make a function. F of n, and what is it doing? It's just doing this. Okay, we're going to return it. Return, okay, and I don't have to do them in order. Now I can just print f of 20. What is it? The nth Fibonacci number. Okay, you're missing a thing. Okay, so the 20th Fibonacci number is 6,765. Okay, the computer is rounding. This is the person who said do NumPy. They led me astray, because look, NumPy doesn't do it perfectly. NumPy only holds 8 decimal places. If you hold infinitely many decimal places, it'll be exactly 6,765. So that's good. So now we have this nice formula. Will it work for f of 100? I'm curious. It might overflow and explode the computer. Let's see. Okay, look. So f of 100 we know is an integer, but the computer cannot store it as an integer. The computer says, look, it's like 10 to the 20. And of course, we could figure out exactly how big it is if we wanted. But look, we're smarter than the computer. We know this exact formula that we got by using linear algebra. The computer can only do stupid stuff like this with only 8 decimal places. So we're smarter than the computer. And this formula is better than the computer can do. So even if the computer can't calculate this to the power of 100, we have this nice formula. I think this is pure magic. So what is the moral of the story? Is eigenvectors and eigenvalues create magic. Did I bump the cord? Okay. Yes. Let's try. Fix the cord. Okay. So I've shown you this. Now we have this cool formula. I think this is the coolest thing in the world. I'm going to show you in a second how it's used on data. But this is a good place to stop. Before we do eigenvectors and eigenvalues on a data science problem, this is, I think, the most pure way to see that eigenvectors and eigenvalues do something special is to do it on some simple thing. And by the way, what we did, all of this stuff with writing it in terms of eigenvectors, that's exactly what the matrix Q and Q inverse do. So Q and Q inverse, these are called change of basis matrix. Change of basis matrix. And they're doing exactly what we did. So instead of having a vector like 0, 1, if you write the vector 0, 1 as this stuff, that's exactly what the change of basis matrix does. In fact, the change of basis matrix in this case has 1 over square root of 5 and minus 1 over square root of 5 next to it. So we really did it this way, exactly the same as it says over here, but we did it in a more kind of hands-on way. This is like the slick way where you don't need to know anything, and this is the like smart way where you see what really happens. Okay. Questions or comments about the Fibonacci numbers? Okay, now let's do a problem that seems completely unrelated, but is also going to turn into the same thing. It's going to turn into eigenvectors and eigenvalues. And so that's why I wanted to start with this, to show you why they're magical. And it's a very simple sounding problem, which is how do we reduce the dimension of our data? How can we reduce the dimension of data? Okay? And just like the Fibonacci numbers seem like they have nothing to do with eigenvectors and eigenvalues, This problem seems like it has nothing to do with eigenvectors and eigenvalues, but it turns out that is the secret way to do it. All right? And so to start with, I'm going to make it a little Desmos. And so here is my data. So I have some data points. The green is the data, and I have one point that I can slide around. And I have this nice data over here. And the problem is as follows. We want to reduce this data down from a two-dimensional data set. Right now there's x and y values, down to just one dimension. And how are we going to reduce it down to one dimension? We're going to apply a linear transformation. So I'm going to take the data and project it. And when you project it, you can choose what direction you want to project it in. Okay? So you take the green data, you project it down. If maybe you want to project it only onto the x values. This is projecting straight down onto the x values. And this is projecting straight onto the y values, like that. Okay? So take your original data, delete the x values, only keep the y values. And the question is, which is the best way to do it? What direction is the best here? Should we do it like this, like that? How should we do it? And I made a little mathematize where you can tell me what is the best direction. And I have two options for you. To pick the best direction, we should either make the points as close together as possible or make the projection of the points as spread out as possible. Which one do you want to do? So do you want to spread them out or put them together? So I guess I'll let you think about it. Sure. So stare at this picture and project the points. Do we want to spread them out or put them together? Which way is better? Okay, I'll let you think for 1 minute. If you saw the videos, maybe you know already what it is. But this is the right thing to think about in our problem. Okay, time's almost up. Let's see what you said. Should we put them together or spread them apart? Okay. What did people say? Woohoo! A 9-to-8 split. This is amazing. So 9 people said we should spread them out, and 8 people said put them close together. This is basically a 50-50 split. Let me show you the two pictures. So spread out is something like this. They're pretty spread out. And then something like this, they're pretty close together. So which do you think is better? To go like that, spread out, or go like this, put together? So now you can see what they kind of both look like. And you can tell me, what do you think is a better way to keep track of the data? Okay, and I will open it up for a revote. Feel free to chat with your neighbors this time. We want to do it again. Okay. Opened up again. Spread out or put together. I showed you some examples. All right, 30 seconds left. Put in your updated guesses. Spread out or clump together. You decide. Okay, What did people say? Time is up. There's like 1 or 2 people who are not in yet. Okay. Let's see. Wait, we had 9 plus 8. We had 17 last time. 2 people chickened out and ran away. Okay. Well, I guess they ran away. What did people remaining say? All right. This time, 12 to 3. Make the projection as spread out as possible. That is the right answer. So we want to spread it out. If you project something like this, all the points look the same. If you kind of like make them as close together as possible, your data set basically says all the points are close to 0. Like you kind of lose all the information that is in these points. On the other hand, if you spread them out as much as possible, that is something like this. And in this situation, the points are very close to where they were originally, right? Like this point over here barely moves. These points barely move. You kind of retain the original structure of the points being spread out like this. And you know they're replaced with these blue points that are one-dimensional, but it's very close to where they originally were. You're not losing a lot of data. Like on the other hand, if you do it the other way, right? Like if you do it this way, this point over here, which is way up there, and this point over here, which is way down here, they look like almost the same point. So you're gonna have mixing up these points. Whereas if you do it over here, there's like no points getting mixed up. I guess there's a couple. Like this point gets mixed up with that point. But those points are very close together, so I don't mind that. This point gets mixed up with that point up there. But again, they're close together. So we kind of lose less information if we're doing it this way. That's why we want to spread them out. And I think you guys figured that out. Any questions about this? This is the big idea over here, is that you want to keep as much information, and keeping as much information means spreading them out as much as possible once you've projected it. Questions or comments about that? Does that make sense? So now the question is, you have this idea, spread them out. How do you mathematically say this? So the idea is spread them out. Where's my pen? Idea. Spread them out. Spread out the points. That's a fun idea. How are we going to measure how spread out they are? How to measure that? How to measure? So like mathematically, in what way is this better than this? I wanted to do it this way. So I can see visually it's more spread out, but how would you measure that mathematically? How would you assign a number that tells you one is higher than the other? Yeah. Variance. The variance. Yeah, very nice. So the simple way to do this is the variance. How to measure? Use the variance. And the variance in this case is exactly proportional to the sum of squares, aka the sum of squares. Well, I guess more accurately, the variance is the average sum of squares. The average sum of squares. So every single point in our little picture, we're going to measure how far it is squared from 0. And then we're going to average that over all the points, and we want to make that as large as possible. And that is exactly what I call the score, the sum of squares. Okay, there it is. And you can see when I turn the line, this can get bigger or smaller. Here, the sum of squares is very small. It's 0.68. And if I rotate this, I can make it bigger. It's getting bigger, 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 bigger. And then at some point, it should reach a maximum. And then it should start to get smaller again. You see how it got smaller again? So I want to make it exactly as big as possible. 0.4646, 67, 68, 69. Oh boy. It's hard on a trackpad. Okay. 64, 65. Okay, 65. Can I beat 65? I think that's it. 9. Okay, I think that's it. That's the maximum. So, but you move this around until it's at its maximum. And mathematically, that is maximize the sum of the squares. So we are going to maximize the sum of squares of projected points. Okay, and now we're in linear algebra land. The projected points and the sum of squares, these are both linear algebra operations. What are the projected points? The projected points are inner products. So these are W dot product with xi. So this is, you take some data point xi, and to find its projection, you do the inner product with some direction W. That's what I was sliding around on my little thing. So let's turn this on. So here are the dot products, and this formula will really just be the dot product of the thing. So as you see, as I turn this around, these are the formulas for how far along the blue line you are. So if this is exactly the x values, it's exactly the x. Oh, this is negative the x value. Okay, hold on. There we go. So it's exactly the x values. if you make it the y values, that'll be the y values, but on the x-axis. So these dot products are the dot product of each green point with this blue line. That's the dot product. And the dot product you can write as a vector. So you can write it as w with x. You can write that as w transpose times x, xi. So you think of xi as a column vector, w transpose is a row vector. That is the dot product. Now we want to do the sum of squares. So we're going to do the sum of squares. Let's call that the SOS, the sum of squares. The sum over all the data points, I equals 1 to the number of data points. And we're doing wxi squared. And so in my language, this is 1 to the number of data points of w transpose times xi squared. There is a really cool way you can write this. And this is, again, this is the magic of linear algebra, is instead of having this little thing with all its components and then squaring them, I can put these all into a big matrix. And so I'm going to write something here, and I'm going to try to convince you that it's the same. It's the same as if you do w transpose times x. And then you do the length of that. Okay, what do I want? W transpose times x, and then I want to do the length of this vector. And here, x is a matrix with all the x's in it. So x is a matrix. What am I going to do? I'm going to stack together all of the x's. So let's do x1 all the way up to xn data. So the number of columns is n data, and the number of rows is whatever the dimension is. In this case, it's 2. So all our data is 2-dimensional. Every single data point is 2-dimensional. And w is a 2-dimensional vector. So w is a 2-by-1 vector. It's a little like 2-by-1 vector, like this. So w transpose, this is 2-by-1. W transpose is 1-by-2. It's a column vector, or sorry, a row vector. 1-by-2. And so if you do w transpose times x, this is a 1-by-2 times a 2-by-n. So when you do this matrix multiplication like this, you get a 1-by-n data vector, and then you do the sum of the squares of the components. That's exactly the norm squared. So this thing equals that thing. This is a vector, a vector of length n data, and then you take its length, the length of this vector. Okay, so what are we trying to get to here? The whole point is all these natural operations that you just look at over here, and you say like, do the projection, take the length. All of these are linear algebra operations, and when you start writing this down, you're going to end up with matrices and vectors all over the place. In this case, W transpose, that's the direction of the line that we're looking at, and X is the matrix that has all our data built into it. All right, now I'm going to do one more thing. Something squared. What is the length of a vector squared? That's, again, just the thing times itself. So if you do, A squared, you could also get that by doing A transpose times A. So now I'm going to do more linear algebra. Look at X, W transpose times, this is a row vector. Hold on. Row vector, I guess it should be like A times A transpose. Multiplied by transpose, okay. W transpose X times W transpose X. Transpose. So this is the formula for the length of a row vector. Formula for the length of a row vector. Okay. And now I'm going to use a formula that says if you do the transpose, you multiply the product the other way. So A times B transpose equals B transpose times A transpose. Okay, and so this becomes W transpose X. Then we got an X transpose over here, and then we have W transposes back to W. Okay, so all of this is to say that the thing we want, the sum of the squares, it just depends on X times X transpose, where X is this matrix over here, the 2-by-n data matrix. This matrix X times X transpose, this is called the empirical correlation matrix. Some of you guys on Project 1 decided to print me a 100 by 100 empirical correlation matrix that took up the whole page. This is what it is here. Here it's a 2 by 2 matrix, the empirical correlation matrix. So this is W transpose times the empirical correlation matrix. Let's call it W. And so this matrix Cij is the covariance. It's the sum of xi, xj over all your data. And that's equal to x transpose. Okay. So for example, the 1, 1 entry is how much the x's go with themselves. So it's the how much x correlates with x1. That's the variance of the x's. And the x22 is the variance of the y values. The x12 is the correlation between the y's and the x's. That's the correlation matrix that appears. All right, great. Now the question is, how do you maximize this? Which vector W maximizes this? That's what we want to do. We want to find the direction W that maximizes this sum of squares. And the answer is, it's the eigenvalues and eigenvectors. So, and one way to write it is write W as a linear combination of the eigenvectors of C. That's what we're going to do. So C, we're going to say it has eigenvectors v1 with eigenvalue lambda 1 all the way up to vk, an eigenvector lambda k. In this case, k equals 2. But W is some linear combination of these. So W equals A times v1, say A1 times v1 plus A2 times v2 plus dot 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 plus AK times vk. So what is W transpose C times W? Well, it's going to be A1 v1 plus dot 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 plus AK vk times C times A1 v1 plus dot 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 plus AK vk. And this thing is transposed. But now the matrix C, when you apply it to the A's and the V's, becomes something very nice, which is it just multiplies by lambda. So it just becomes A1 lambda 1 times V1 plus dot 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 plus AK lambda k times Vk. So this is the same kind of trick we used in the Fibonacci numbers, which is the matrix C in general is really nasty. Like, what does it do to this thing? We have no idea. But if you do it on the eigenvectors, then it's so simple and so nice. And what does this become? This becomes A1 squared times lambda 1 plus A2 squared times lambda 2 plus dot 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 plus AK squared times lambda k. And the reason is because you can make sure the eigenvalues are orthogonal. Can ensure the eigenvectors are, this is called orthonormal. So because they're orthonormal, you get this really nice formula. So it looks like some crazy problem of like which direction should you take to maximize this thing, but it just turns into a really simple sum of whatever the components you did, they should add up multiplied by the lambda ones. Okay, and so what's the answer? Which direction is the best? Well, you should just make, if lambda 1 is the biggest eigenvalue, then make this as big as possible. If lambda 1 is the biggest eigenvalue, then set A1 equals 1 and all others 0. So this problem that looked impossible, how do you maximize this thing, turns into something very simple, a simple linear combination of the eigenvalues. And you can see if you want to make it as big as possible, you should just make this thing as big as possible. This idea, by the way, is called the Rayleigh quotient. The Rayleigh quotient, if you've seen it before, and if you had a good linear algebra class when they talked about eigenvectors and eigenvalues, they would have told you about the Rayleigh quotient. This is for positive semi-definite matrices. And this is why it works. Okay, so what's the answer? The final answer the best direction is the largest eigenvalue. Best direction is the eigenvector that has the largest eigenvalue. Okay, so that's the final answer. And we can check in our little demonstration. What this is saying is if you compute this matrix, C that I told you to compute, and you compute the eigenvectors, there should be an eigenvector of the matrix C that points in this direction, and that's the best direction to go. So let's check if that's true. I'm going to do it in NumPy in a second, but maybe I'll pause here because I was going a bit quick. So if there's any questions or comments about this linear algebra stuff, again, this is why they make you take linear algebra in undergrad. So they say, like linear algebra, maybe they don't tell you why. They just say, do all these calculations, learn all these rules. Like learn that when you do a transpose, that things transpose. All these silly rules. They probably just made you memorize them, but now you know why, because it's super useful for solving hard problems and understanding hard problems in terms of simple things. Any questions or comments about this? Okay, let's see this in action in our particular example. So I made a version, an exact version of this data set. I made it in, not in Desmos, but in Python. So it looks like this. Here it is. So here's data with two features, and it's exactly the same kind of thing as before. It was generated in the same way as I generated the data in Desmos. So there's some line like this, and we know we want to project onto this direction, but we're going to do all of the steps that I did sort of theoretically. We're going to do them in practice now. Okay, and here is the function that we are trying to minimize. This is the norm of xw squared. That's exactly the thing that we're trying to minimize. So remember, in our linear algebra, we said the thing we want to minimize is the sum of the squares, and the sum of the squares is this guy, xw squared. I wrote it the other way in Python, but it's exactly the same thing. Okay, the norm of xw squared. So make that as big as possible, and these are the level lines. This is exactly what we saw when we were doing 3D Desmos with those wide valleys. So very close to here, this is the minimum at 0. If you put in w as the 0 vector, you get 0. If you go in that direction, that's like going up a steep cliff. So the values change very quickly. You get really high values. If you go this way, it's almost flat. You don't get much. And our job is to maximize it. So which direction W should we pick to maximize it? We should go up the hill as steep as possible. It's that direction. It's actually this red line, or the opposite of this red line. They're both the same. That is drawn here. And that red line is actually computed by doing the eigenvectors of the matrix, of the correlation matrix. So here are the eigenvectors. These two red directions are the eigenvectors. Like I said, you can make sure they're always orthogonal. In this case, that means they're just perpendicular. And they perfectly tell you the directions the data is living in. And then if you do the transformation, that's transformed to the coordinates where you, instead of looking at the original data points, you just look at what is the component in this direction, what is the component in that other direction. Then the data looks like this. So this is the transformed points where the y-axis is the largest eigenvector, so spreading out as much as possible, and the x-axis here is the second eigenvector, whatever is left over. And so you can reduce the dimension of the data by just deleting this x-axis and keeping the axis where things are spread out as much as possible, and that will give you most of the information about the points. So that's exactly the same idea as in this picture that we said of finding a line that looks like this direction. It's exactly the eigenvector direction. And yeah, I think this picture, if you understand these contours, which I've been trying to show you the last couple classes with the lost surface, it's the same kind of idea. You want to make it as large as possible in this case, which is going in this direction. Okay, questions or comments about this? So this is all the theory of why this stuff works and why the eigenvectors and eigenvalues come up, and why you want to transform along the eigenvectors and eigenvalues. Next class, we're going to have lots of examples, kind of like working on this in practice and how you really apply it to things. But hopefully this has helped you understand what is the point of the stuff and when will it work and not work. Like what happens if these things are not in the line at all, but if they're in a big circle? What would this thing do? And you would see it doesn't do much. So hopefully that helps. Let's finish the class with one more question that we're going to start the class off with next time. and this is about comparing countries. So here I have 4 countries, and I have 12-dimensional vector, or however many of these things there are, for each of these 4 countries. And one of these countries is not like the other. One of them is the odd country out. And if you stare at this for long enough, you can maybe convince yourself what is the odd country out. And next class, I'll show you how to do it in 1 second using what we learned today. So using the theory of what we learned today, that largest eigenvector, you can tell which of these countries is the odd one out in like 1 split second. But I thought I'd make you do the hard version first, which is to stare at this and try to figure out which one is the odd country out. And I will let you guys think about that. Once you answer, then we'll stop and we'll take it up next class. So tell me which country is the odd country out, and I'll show you how to do it with the theory that we just did next class. Okay, so we'll stop there. Once you finish this question, you can go, and we'll see you guys on Wednesday. Okay, and I guess you can have